Okay, then let's start with class 12 physics, that is chapter 7, alternating current. Chapter 7, alternating current. Let's start with this. Now, let's start with introduction here. We have so far considered direct current sources and circuits with DC sources. These currents do not change direction and magnitude with time, but voltages and currents that vary with time are very common, and these are called as AC currents. The electric mains supplied in our homes and offices is a voltage that varies like a sine function with time. Basically, AC currents are currents which vary with time. Basically, they will change direction every periodic amount of time. And sine function is used to denote at which function, like at which certain time, at which instant of time, how much the voltage is there. Like if we see a sine wave, this is a sine wave where this is 0, this is pi by 2, this is pi, 3 pi by 2, and finally 2 pi. This is a sine wave function, and based on this we can identify if it was, let's assume, voltage, then every second, or let's assume current. If this is current, then every second it is going to vary, and when it is 0, the current is at time 0, current is also going to be 0. After some time it will be at peak value, then again come to 0, then peak value again but in the opposite direction, and again come to 0. This is called an alternating current. It will change. Alternating current definition is a current which will change directions which will differ in magnitude continuously and change directions periodically. Such a kind of current is called as AC current, and it varies like a sine function. Such a voltage is called alternating voltage. In case of voltage, it is alternating voltage. If we are talking about current, we talk it as alternating current. The current driven by it in a circuit is called the alternating current, AC current. Let's see something. There is a star here, meaning there is a note. The phrases AC voltage and AC current are contradictory and redundant, respectively, since they mean literally alternating current voltage and alternating current. Still, the abbreviation AC to designate an electrical quantity displaying simple harmonic time dependence has been so universally accepted that we follow others in its use. Further, voltage, another phrase commonly used, means potential difference between 2 points. Okay, it's just why we use that word. Alternating current, like it's a universally accepted term, alternating current, for describing an electrical quantity that is displaying simple harmonic time dependence. Basically, it's going to vary with respect to time, and it is similar to simple harmonic motion, and so it is universally accepted to call it as alternating current. Okay, that's what they're saying. Today, most of the electrical devices use we use require AC voltage. This mainly because most of electrical energy sold by power companies is transmitted and distributed as alternating current. The main reason for preferring use of AC voltage over DC voltage is that AC voltage can be easily and efficiently converted from one voltage to other by means of transformers. Further, electrical energy can be transmitted economically over long distances. Okay, basically, why there is a need or use of AC current, alternating current? Why can't we just use DC current? DC is direct current, AC is alternating current. Why can't we just use DC current and be done with it? Why we need specific AC current? Why we need it? Because one thing, AC current can be easily transmitted like with DC. Let's come with DC first. If we take a transmission line, long kilometers of wires carrying current, DC current for going through such large distances, it there will be very high energy losses. Much of the current will be lost because of heat and many other such factors, and current cannot be easily transmitted for very long distances through AC current, I mean DC current. But if we take AC circuit, that is alternating current, we can transport current or we can produce current through transmission lines, transport current through transmission lines without much energy loss, which which is very efficient, economically efficient, meaning like there won't be much energy losses. And one more thing why we use AC current is because we can manipulate the voltage. Normally when we see in transmission lines, the voltage is very high, but in our homes the basic voltage is 220 volts and 50 hertz. That is basic voltage in India. So for us to if we use such, we need that much. And with the use of transformers, we can easily convert the 10,000 volts of current from transmission line into 220 volts, that is through a step down transformer. Or we can even increase it. In other cases, in case of home, we need to reduce the voltage. In case of power station production plants, we need to increase the voltage. In such a case also, you can use a step up transformer to increase the voltage of the current. So this can be done only through AC currents. DC currents, it's not very efficient. It's not possible. So AC currents, the two main uses are long transmission, and we can easily manipulate the voltage. AC currents exhibit characteristics which are exploited in many devices of daily use. For example, whenever we turn our radio to a favorite station, we are taking advantage of a special property of AC circuit, one of many that you will study in this chapter. Okay. Before going to the next topic, let's see something given about Nikola Tesla. Nikola Tesla from 1856 1943. He's a Serbian American scientist, inventor, and a genius. He conceived the idea of the rotating magnetic field, which is the basis of practically all alternating current. Maybe they are talking about the AC generator, where there is a coil, basically an armature, which will rotate. Mechanical work is done, and through which an AC current is produced due to changing magnetic flux. The rotating magnetic field, which is the basis of practically all alternating current machinery, and which helped usher in the age of electric power. He also invented, among other things, the induction motor, the polyphase system of AC power, and the high frequency induction coil, the Tesla coil, used in radio and television sets and other electronic equipment. The SI unit of magnetic field is named in his honor. That is, the SI unit of magnetic field is called as Tesla, denoted by T, that we have studied much more in our previous chapters. And I don't think there is much about the magnetic field in this chapter. Okay, let's start with the first topic, that is AC voltage applied to a resistor. We are going to talk about a pure resistive circuit here. When if we connect an AC circuit, I mean if we connect an AC current supply, this is the denotion of a AC current supply. We denote it by circle and a varying, or a basically a wave. This is the symbol. Instead of battery, where normally we have battery with one long and one short electrode, but in this case we use this one. This is the symbol for the AC supply. This is the AC supply, which is basically acting as a current source. And if we connect this to only a resistor, first is a pure resistive circuit, And if we apply this AC voltage to a pure resistor, what are the differences when compared to direct circuit, and what is the efficiency and all we will see here. This figure shows a resistor connected to a source of, this is E, which is a EMF, that is electromotive force, or basically potential difference. AC voltage, we are talking about an AC voltage, it is a time varying potential difference. It shows a resistor connected to a source E of AC voltage. The symbol for an AC source in a circuit diagrams is this one, as I told. We consider a source which produces sinusoidally varying potential difference across its terminals. Let this potential difference, also be called AC voltage, be given by this one. Okay, as I said, this we consider a source. It's a source which produces sine function varying potential difference across its terminals. Meaning, it depends on, if one at certain instant the potential is in this direction, it will again next instant it will again change and turn into this direction. It will keep on varying. Again, it will turn here, and again here, depending on time. That is time varying sine function. It will the sine, basically with sine function we can identify at which time or which area and how much at which instant the current is maximum or minimum, or how much the current is there or how much the potential is there. We can identify that with using a sine function. We consider a source with which produces a varying potential difference across the terminals, and if we consider this as a potential difference, also called as AC voltage, and this AC voltage is equals to V, which is equals to Vm sine omega t. Basically, we know that this is actually from a previous chapter, like electromagnetic induction, their AC generator derivation. From that derivation we got this one. This is basically the voltage produced in an AC generator formula, same formula, but we got current. But if we multiply with, or we do something with resistance, we will get V, which is equals to Vm sine omega t, where Vm is the peak voltage or the amplitude of the oscillating potential difference. Basically, if we take, as I said here, this is a sine wave, and if we take its potential difference, this value, which is called as, if we take this is current, not potential difference, we call it as Im or I naught. The peak value, the highest value here as well, different direction, but magnitude wise, these peaks are called as amplitude of the wave, or basically the peak voltage or peak current, the maximum current in the whole cycle or in the whole half cycle, where Vm is the amplitude of the oscillating potential difference and omega is its angular frequency. We can write omega, which is equals to theta by t, and omega t, which is equal to theta. In place of sine theta, they substituted omega t because of this reason. AC voltage applied to a resistor. To find the value of current through the resistor, we apply Kirchhoff's rule, that is KVL, or potential voltage rule or loop rule, where like the Kirchhoff's rule states that, like, through a closed loop the potential difference will always remain zero. The total potential difference across a closed loop will always remain zero. That is the Kirchhoff's loop law or loop rule. This is basically what I said. To the circuit shown, this we saw in like chapter 3, that is current and electricity. Okay, we won't go for that. We only need to use it. Now we apply it. When we apply it, we take it as, Let's go to word. AC current. Okay. Okay, then let's continue. AC current. Okay, then let's continue. From Kirchhoff's rule, that basically says the voltage in a closed loop will always be zero. The total net potential difference in a closed loop will always be zero. Now using this, basically we write the potential, that is the AC circuit potential, E minus the potential, let's assume at any instant of this AC circuit, let's assume there is a current in this direction at an instant. This is an instantaneous current. A current will be going like this, let's assume that. And if we consider, if that was the case, then the current will be in this direction. Now let's take r direction from, also in this direction, r direction, and current direction in this direction. In case of a resistor, it will be minus IR, the potential will be minus IR, which will be equal to 0, and E, which is equals to IR. And from this equation, we know that the potential difference formula is equals to E or V, which is equals to Vm sin omega t, that we substitute here in this equation. E value we substitute. Now if we want to find out the current, we just shift the peak voltage, or I mean the current, I mean the resistance this side. We will get the current, which is equals to potential by R sin omega t. R will remain constant, it won't change with, it's not a varying function of time. Here in case of AC circuit, both potential and voltage are a function of time, they vary with time, but resistance is constant here, it won't change. Since R is constant, we can write this equation as Im sin omega t, where Im is the peak value of the current, where the current amplitude Im is given by V peak value by R. Equation 7.3, this one is based on Ohm's law. Ohm's law states that potential difference across a circuit is directly proportional to current. So based on that, R is a constant in that equation, and we can get current, which is equals to potential by R. This is Ohm's law, which is for resistor, works equally well for both AC and DC circuits. Basically, even if it's alternating current or direct current, for both of them, it will work equally well. The voltage across a pure resistor and the current through it, given by equation 7.1 and 7.2, are plotted as a function of time in 7.2. These equation, basically this equation, which is potential, which is equals to, not that one, this one, potential, which is equals to V naught or Vm, that is the peak value of potential, times sin omega t, and our derived equation for current in a pure resistive circuit, that is I, which is equals to Im sin omega t. They are plotted as function. We just plot them a graph, in a graph. This is omega t varying omega t, that is angle. Let's assume this is potential or I naught. If we check, they are same wave function, but like different amplitudes, where the amplitude of the potential is higher, slightly higher than current, but they are pretty much varying equally with time. Like if we take at around pi, both are 0. At 2 pi, both reach 0 again, and at pi by 2 here, they reach peak value, both of them, at the same interval. Note in particular that both V and I reach 0 minimum and maximum values at the same time. So clearly, okay, we are going to see something here. Clearly the voltage and current are in phase with each other. It is important to see this in phase meaning both have variations, same kind of variations at same kind of time. That's what you mean by in phase. In a pure resistors, the voltage and current are in phase. The minima, 0, and maxima occur at the same respective times. We see that like the applied voltage, the current varies sinusoidally and has corresponding positive and negative values during each cycle. Thus, the sum of instantaneous current values over one complete cycle is 0 and the average current is 0. The fact that average current is 0, however, does not mean that the average power consumed is 0 and that there is no dissipation of electrical energy. Okay, what they are saying, let's see what they are saying first. The current varies with respect to the sign function and has a corresponding positive negative values during each cycle. Like if it's above here, it's positive, it's negative. What this positive negative means is that if at certain time it's going clockwise direction, at another point of time it will go anti-clockwise direction. This is represented as positive and negative mathematically. As we cannot represent anti-clockwise clockwise in mathematical expression, we express it as positive and negative. That is all the difference between maximum and minimum. In terms of magnitude, both the peaks are equal in magnitude, but they are just in opposite direction. And the current, okay, that has corresponding positive negative values during each cycle. And because of this, if we take the total cycle, the whole cycle, if we take, the total current will remain 0 because we have a maxima here and a minima, both magnitude is same. Because of that, the total current on average in one whole cycle will always be 0 in this case. If it's a sine function, it's a sine varying function. In this whole cycle, the current will be 0. The average current will be 0. But that does not mean that the power, like an electrical energy which we consume for making an alternating current is 0. That is not the case. There will still be electrical loss. We just, when we take a full cycle, it will come, the full average current will be 0. Um, However, that does not mean that average power and electrical energy consumed is 0 and there is no dissipation of electrical energy. There will be dissipation of electrical energy. As you know, Joule's heating is given by I square R and depends on I square, which is always positive, whether I is positive or negative. Basically, we know the law of Joule's heating, where the heating or energy dissipated is directly proportional to I square, resistance, and time. If we consider only I square, no matter, like if we know that like heating is directly proportional to I square. So what this means is, even if the value of I is negative, meaning in reverse direction, the heating will still be there because it will get converted. I mean, not I cap. It will get again converted to positive value because it's a square function. Even if it's negative, positive, both same thing. There will be always a current. I mean, there is always be heating. That is what they mean by it is directly proportional to I square. That is what they are telling. No matter, in logical sense, if we see, no matter if the current is going forward direction or backward direction, it is going through the wire and it is passing through some resistance, due to which there will be some loss of energy and it will be dissipated as heat. No matter like if it's going forward or backward, it's still moving. So only thing that matters is it is moving, and mathematically it is represented as directly proportional to I square. So no matter the direction of the current, it will still be some loss of energy and not on I. It does not depend on I. Thus, there is Joule heating and dissipation of electrical energy when an AC current passes through a resistor. There will be Joule heating and dissipation of electrical energy when an AC current passes through a resistor. Now, the instantaneous power dissipated in a resistor which is equals to P, which is equals to I square R, which is equals to I m square R sine square omega t. Okay. Basically, if we want to find out the uh, the power dissipated in an AC circuit, we know the power formula, which is equals to I square R. Now we know I from the previous pure resistive circuit, which is I, which is equals to Im or I naught sine omega t. Now substituting this here, we will get power which is equals to Im square R sine square omega t, because it is whole square, I whole square, and power which is equals to Im square R sine square omega t. That is basically what they have written here. The average value of current over a cycle is the average value of P, that is over a cycle, which is less than I square R. No, it's brackets, it seems. The P, which is equals to I square R or Im square R sine square omega t. That is the power dissipated, where the bar over a letter here P denotes its average value, because power dissipated will not be uniform in a AC circuit. This bar here, it is represented by not P but P bar. This bar here represents that it is an average value, and this bracket here, this greater than less than kind of symbols used here, these brackets denotes taking average of the quantity inside the bracket, since Im square and R are constants, but sine square is not. We take average of the values, and because peak peak current will always remain constant, there will only be one peak for a certain voltage, for a certain varying voltage, so the peak value will remain constant, and resistance, we also know that it will remain constant. So the only thing that is varying is sine square, or the sine function, sine square function, sine square omega t. So P average, which is equals to I m square R, and varying sine square omega t, using the trigonometric identity that sine square omega t, which is equals to half 1 minus cos 2 omega t. We have sine square omega t, which is equals to 1 by 2 1 minus cos 2 omega t, and since cos 2 omega t, which is equals to 0, we have sine square omega t, which is equals to 1 by 2. Thus P value, which is equals to half Im square R. Okay, they gave a power average power equation, which we got it as half Im square R to express AC power in the same form as DC power. P, which is equals to I square R. A special value of current is defined and used. It's called root mean square, or effective current, and is denoted by IRMS or I. Okay, if we want to we if we want to write or express power dissipated, energy dissipated, or whatever it might be, we need to convert or understand AC power in terms of DC power, so it might be easier and it's better that way. So for because of this need that AC power uh, should be understood easier, we define a specific root mean square value, that is RMS value, that is IRMS. This IRMS is the effective current. Effective current meaning it is the for a AC current, the equivalent value of DC current is called as IRMS value. It is the effective current in terms of DC current. The RMS current is related to peak current Im by I, which is equals to, we just divide peak current by root 2. Then we will get the RMS value. When we divide the peak current value by root 2 or peak voltage value by root 2, we will get VRMS and IRMS value. Similar to IRMS, VRMS, that is root mean square of potential, is also the equivalent AC potential, which is over a period of one cycle equivalent to DC current or DC potential. IRMS value is the current over a single cycle, which is equivalent to DC current. Now I, which is equals to, it is defined by basically dividing by root 2. As I said before, we just divide the peak value by root 2, we will get the IRMS value. In terms of I, the average power denoted by P, which is equals to P average, which is equals to 1 by 2 Im square R, which we can write as I square R. It seems this actually might not be a 1 by 2, but it is 1 by root 2. Yes, it's most likely 1 by root 2. I will check it later, but it's most likely 1 by root 2. 1 by root 2, if we divide I square m by root 2, we will get I square, which is the RMS value. That is what they have showed here, where we know power average, which is equal to, in AC circuit, power average is equals to I square R. But in I mean I naught or I square I naught square R by root 2. This is the peak value, I mean the power dissipated in an AC circuit. We can convert this using this formula, that IRMS value is equals to I naught or Im by root 2. We can convert it by writing it as, actually it might not be this one. So we can't write root 2 as root 2. We can't divide root 2 for two I naughts, that is, we have a square here. So that means they probably wrote 2 as root 2 times root 2. Now we have two root 2's for both I naught, and we can convert P, which is equals to IRMS whole square times R. This is the average P value, or we can write it in terms of voltage as well, where P, which is equals to VRMS times IRMS. Or this is exactly the same formula in DC current, where P, which is equals to VI, voltage times current. Here it is RMS value, which is same as DC value, so the formula will become accurate. Okay, let's continue. Similarly, we define RMS voltage as I showed before, like we divide like peak value of RMS, I mean we divide peak voltage value by root 2, we will get VRMS value. And this RMS value of, and basically what RMS value of peak voltage is, I mean the voltage is, it is basically the DC current equivalent of an AC current uh, potential difference. That is what we call an RMS value, where V which is equals to Vm by root 2, which is 0.707, or basically 70% of peak value. From 7.3 we get that Vm which is equals to IMR. Using Ohm's law, basically we define that peak values where R is a constant, we can define Vm which is equals to IMR, and we can also define, basically dividing them by root 2, we can get V which is equals to IR, where these are RMS values, and actually this is DC value, so this is also already proved using Ohm's law. Nothing new, just a repeat, but just a new term that is called RMS. And the denotion or convention of denoting RMS values is, we denote RMS values as just writing VRMS or IRMS, or simply write V or I, V and I. If there is nothing in the subscript, or if there is RMS in the subscript, it is RMS value generally. There is a convention to denote this. As for peak values, we denote them either by Vm and Im, or we can denote them as V0 and I0. These are all conventions for denoting peak values. Basically, this is a peak value, and RMS values are denoted without a subscript or writing RMS as a subscript. Okay, leaving that. Vm by root 2 is equals to Im by root 2R. Okay, we got this equation. Now this equation gives the relation between AC current and AC voltage and is similar to that of the DC case. This shows the advantage of introducing the concept of RMS values. In terms of RMS values, the equation for power and relation between current and voltage in AC circuits are essentially the same as those for the DC case. That's what I said. We are taking an equivalent of the DC power and all. So basically, it should be working even if it isn't exactly the same. We should get the same values at least, because we are taking an equivalent. It is customary to specify RMS values for AC currents. For example, the household line voltage of 220 volt is an RMS value with a peak voltage of 311 volt. Okay, the in India the peak voltage, which is, I mean, the line or the voltage we get at homes is 220 volt and 50 hertz. In that value, 220 volts is actually a RMS value. It is not the peak value, it is the RMS value. And if we calculate the peak value, it should be around 311 volt. And 220 volt is actually only the RMS value. In fact, the I or RMS currents in the equivalent DC current, that would produce the same average loss as the alternating current. That is what is basically the use of RMS current. The IRMS current is equivalent DC current that would produce same average power loss as alternating current. Basically, the IRMS value will produce same energy loss, as we know that energy loss depends on I square, and basically it means that it depends on current. So the IRMS current will, if we calculate the IRMS current value, it will give the same power loss as in DC case and alternating case as well. Okay then, and we can also write the equation as P which is equals to V square by R, or IV, since V equals IR. Just the known formulas getting repeated here. Anyway, let's see an example. A light bulb is rated at 100 watt. Watt is the unit of power for a 220 volt supply, and this 220 volt is the RMS value, not because they have mentioned specifically that the convention. I said before that 220 volt in India is an RMS value. It is essentially because of that also, but mainly in a question they did not specifically mention V naught value, so that means it must be an RMS value. 220 volt is an RMS value. Now a light bulb is rated at 100 watt for a 220 volt supply. Find the resistance. First thing we need to find resistance of the bulb, then peak voltage of the source, and RMS current through the bulb. Okay, they clearly ask peak voltage. That means this voltage is obviously RMS value. Now let's see the solution. We are given P which is equals to 100 watt and V which is equals to 220 watt. Now we know the previous formula, which is V square by R, which is equals to power. We just substitute the formula like this, and basically substituting values, we will get the resistance of bulb as something as 484 ohm. Now the second question, the peak voltage of the source, that is basically we know that Vrms, which is equals to V naught by root 2. When you want peak value, V naught which is equals to Vrms root 2. That's all. When you multiply it, we know that you will get somewhere around 311 volt. Now the next question, they asked IRMS current. We know the formula P equals IV, and IE here is the RMS value, and in such a case I which is equals to P by V, and we will get 0.454 ampere as the RMS current. And if you want peak value, if they ask something like peak value of find the peak value of current, then we just multiply this RMS value with root 2. We'll get some 0.7 or something here if I multiply. Now okay, then let's go to next topic, representation of AC currents and voltage by rotating vectors. Now this is a new concept. Basically, how do we represent or rotate AC current and voltage? The first way we saw that was through this kind of graph, where we represented this is a graph of V, that is voltage, and I versus Vt, I mean omega t, that is the angle. Now this is the first graph we saw for representing voltage and potential difference. This is basically a sine wave, and we saw the representation here. There is a one way of representing potential difference and current in an AC circuit. Now the second way is through a phasor diagram for this circuit. Phasor diagram, we have two terms. One is a phasor and the second is a phasor diagram. What is a phasor? Phasor, or whatever we pronounce it, it is a rotating vector. Basically, it's similar to position vector. If we take, it's not exactly same as a position vector. If we take this as the origin, I mean this as the axis. If we take some kind of let's take a point here. Now this is a position vector. This is a position vector here. But let's assume this if this vector, this position vector, is rotating with an angular velocity omega, at such an instant when the position vector, vector similar to a position vector, is rotating with an angular velocity omega, then that is called a phasor. It's a rotating vector. A vector which rotates with angular velocity omega is called as phasor, and it will always be from the origin. It will always be attached to origin. There is no something like this. No, it won't be like that. It will be attached to, represented through, attached to the origin. That is a phasor. And this whole diagram, in this case, if we see this is a specific circuit, there is, if we have two phasors here, there is phasor of the I, that is current, and phasor of the voltage. We know that both voltage and current are varying. They are varying with time. Basically, that is what this graph shows. Both are increasing, decreasing, reaching zero, decreasing again, then increasing again. Meaning they're constantly changing with time. That means both should have a vector. I mean, both should have a phasor. Both are rotating like this with angular velocity omega. But if we see here, in a pure resistive circuit, we saw something about the NCERT saying that in pure resistive circuit, the current and potential are in phase. What does that mean? We saw that it means that at a certain instant of time, both values reach certain peaks, or like in case of here, if we see at pi by 2, both reached peak. At pi, both reach 0, and at 3 pi by 2, they both reach the absolute minimum value. That means they are having same kind of variation with respect to same kind of time interval. That is what we mean it is in phase. And in phasor diagram, we can see this clearly. They are attached together, there is no angle difference between them, and they are rotating together, meaning they are reaching their needed peaks. Their peaks are at different level, as represented here. This has a higher magnitude peak. It doesn't matter, it does not uh, specifically mention anything. It just has a different values. Even if they have different values like this, they are rotating together. That means they are varying equally at same instant of time. That is what is essentially represented in an phasor diagram. Now we saw pure resistive circuit. Later we are going to see the this graph and phasor diagram of pure inductive circuit, where we have a inductor, or basically a coil, free coil, which does not offer resistance but which will have self inductance. And there is another way, that is another one, another coil, another circuit which we'll see is a pure capacitive circuit, which has a pure capacitor only. It does not have resistance or inductance. It only has a capacitor. These are three individual pure circuits. Next we have a combined circuit of a series LCR circuit. That is, we have inductor, resistance, and capacitor in series connected. Now there also we will have a phasor diagram, which is essential to understand or easily understand this. Now that's with those kind of diagrams. Now let's come back. Let's start with the phasor topic. Representation of AC current and voltage by rotating vectors, the phasors. In the previous section, we learned that the current through a resistor is in phase with the AC voltage. But this is not the case not so in the case of an inductor, a capacitor, or a combination of these circuit elements. In order to show phase relationship between the voltage and current in an AC circuit, we use the notion of phasor. Basically, if in all kind of cases, like in case of all the circuits I said, like an inductive, capacitive, or a LCR circuit, if both current and uh, voltage are in phase, what is the use of a phasor diagram? If all kinds of circuit it's the same value, there is no need for specific representation. It can be just understood. So why we need a phasor diagram is that is not so the case as in other circuits. No, the variation of, or basically let's just say the current and potential are not in phase. There will be difference, or we understood what in phase means. Now we need to understand what out of phase or not in phase means. In phase means first in phase, it means like they are varying equally at particular instants of time. Now not in phase means at certain instant of time they are not varying equally. They're not varying equally. That means in phase here both are reaching peak value at the same time, but not in phase means maybe current is reaching peak value at this kind of position. Like if it was something like this, if the let's say I'm drawing the graph of current. If let's just say this is a graph of current, which we will see later. Now this is, in this case we can see clearly that they are not in phase, meaning at this position, that is at zero, current which is having a minimum value, whereas the potential is zero, and at pi where the potential is zero. Wait a second, that's not the case. Okay, this is correct. It might not look very good, but let's just understand it for now. Okay, this is the current graph. At pi by 2, at zero position, current is at the minimum value in this graph, and potential which is at zero, it is zero. And next, at pi by 2 position, voltage is at peak value, whereas current is zero. And as potential is decreasing and reaches pi where it reaches zero, now current will become peak value. This kind of variation, which was not seen in the previous circuit, was, that means they are not in phase right now. This is what it means. Like this is one case where current and voltage are not in phase. That is what I wanted to say. Now let's continue reading. In order to show phase relationship between voltage and current in an AC circuit, we use the notion of phasors. The analysis of an AC circuit is facilitated by the use of phasor diagram. They provided a star mark here. Let's see what that is. Though voltage and current in AC circuit are represented by phasors, I'm reading here, rotating vectors, they are not vectors themselves, they are scalar quantities. It so happening, it so happens that the amplitudes and phases of harmonically varying scalars combine mathematically in the same way as do the projections of rotating vectors of corresponding magnitudes and direction. The rotating vectors that represent the harmonically varying scalar quantities are introduced only to provide us with a simple way of adding these quantities using a rule that we already know. Okay, how can we represent them, the like potential and current, as vectors? We saw that phasor is a rotating vector. It's a vector somehow. So we already know from previous chapter that current and potential are not vector. They're purely scalar quantities. They're completely scalar quantities. But now we are representing them with vectors. So basically, we are not changing the essence of voltage and current into vectors. They are still scalar. Basically, what we are representing through a phasor is the changing in magnitude of a scalar quantity. The continuous changing in magnitude of a scalar quantity is being represented as a phasor diagram. It is harmonically varying scalars which seem to mathematically combine in same way as rotating vectors do. So this is just for mathematical ease that we make them or represent them as vectors, but they are still scalars. That's what they're trying to say. A phasor is a vector which rotates about the origin with angular speed omega. As shown in figure 7.4, the vertical components of phasor V and I represent the sinusoidally varying quantities V and I. The magnitudes of phasor V and I represent the amplitudes or peak values, okay, of these oscillating quantities. Now this figure 7.4a shows the voltage and current phasors and their relationship at time t1 for the case of an AC connected to a resistor, that is corresponding to the circuit shown in 7.1. The projection of voltage and current phasors on vertical axis, that is Vm sin omega t and Im sin omega t, respectively represent the value of voltage and current at that instant. As they rotate with frequency omega, curves in figure 7.4b are generated. From 7.4a, we see that phasors V1 and V and I for the case of resistor are in the same direction. Is so for all times. This means that the phase angle between the voltage and current is zero. Basically, what I just said before all have been repeated here. Anyways, now let's see the inductor circuit. AC voltage applied to an inductor. We know what an inductor is from the previous chapter where basically this is an inductor. It's nothing special. It's just a coil. It's just wire wounded in the shape of a coil. Why it's wounded in the shape of a coil? To increase the magnetic field produced. To increase the magnetic field produced, if there is more magnetic field produced, because it is an AC current, because there is constant change in magnitude as well as direction, even though there is no physical changing of position of the vectors, or I mean position of the coil, or area or anything similar to that, because it is an AC current, without any change in configuration of the coil, there will be a constant magnetic change in magnetic flux, because of which there will be self inductance seen here. And this self inductance will always be in the opposite direction of the current. If this AC circuit is providing a current in this way, which is constantly increasing current, continuously increasing current at this instant, like let's assume it's starting from 0 and increasing like this. In such a case, the inductor, due to magnification of the change in magnetic flux, they will produce a current in this side. This is the induced current. According to Faraday's law, it is, we saw the change in magnetic flux which produces an EMF in the opposite direction, where EMF is equals to minus d phi by dt. This minus indicates the direction which is the opposite to the flowing current. Okay, that's that. Now that's what an inductor is, and it is represented by L, that's the inductance. L is an inductance value. And one more formula before reading this is a formula of EMF, where basic, or actually it's not EMF, it is formula of magnetic flux. Magnetic flux formula, it is BA cos theta, but we can also write phi, which is if we consider theta to be constant, we can just write it as BA phi, which is equals to BA, where phi is magnetic flux. And if another formula for magnetic flux, which is equals to L into I, where L is the inductance, I is the current. L is the inductance, I is the current. This is an important formula for with respect to this derivation. and L here is a constant. L is constant, and in case of an AC circuit, we know that I will be continuously and periodically varying in magnitude and direction respectively. Now with that, let's continue. Now this figure, let's see the description of the figure. An AC source connected to an inductor. Shows an AC source connected to an inductor. Usually, inductors have appreciable resistance in their windings, but we shall assume that this inductor has negligible resistance. Basically, we saw the prior one where it has pure resistive circuit, where it didn't have resistor nor a capacitor. I mean, it did have a resistor, it didn't have an inductor nor a capacitor. But in this case, this is also a pure inductive circuit, meaning there is neither a resistor nor a capacitor, only an inductor. But we know that this inductor is made up of a coil, and this coil must be made up of a material, and this material needs to offer some kind of resistance. There will, in reality, there will always be a resistance in materials, but for our case here, let's assume this inductor does not have a resistance, or basically we can consider it as negligible resistance. It offers very low resistance for our pure inductive case. That's what they're saying here. Thus the circuit is purely inductive AC circuit. Let the voltage across the source, which is equals to V, which is equals to Vm sin omega t, the basic equation that we saw before. Now use Kirchhoff's loop rule. Basically, the loop rule which says that the potential difference across a closed loop will always remain zero. Now that is the formula, the sigma E, where the total potential is added, it will become zero. And since there is no resistor in the circuit, we know the formula here. Basically, why we got this is because we know that the in KVL we apply E minus E1, which is equals to, or E1 minus E2, which is equals to 0, and this E1 is the potential difference due to this inductor, and this one we know E1 we can find out through Faraday's law, which is equals to minus d phi by dt. And what is the formula for phi? We just phi, that is this one, we use this formula. In this case, we will get E1, which is equals to, and I already told you that L will be taken constant, and minus di by dt, as its L is a constant, as I told before, it will come out of the differentiation, minus L di by dt. This is the formula. This is the formula for E1, or EMF1, electromotive force 1. Now that is why we have this one here, V minus L di by dt, which is equal to 0. That's how we got that. Where the second term is a self-induced Faraday EMF in the inductor, and L is the self-inductance of the inductor. The negative sign follows from the Lenz law. What Lenz law? What is Lenz law? Lenz law states that the current produced, or the current induced through a changing magnetic flux, will be always in the opposite direction, which resists the uh, change in magnetic flux. Basically, if there is a coil like this, if we assume it's a closed coil and there's a magnet coming this way, if there is a magnet coming this way, the current will be induced in such a way that it will oppose the change in magnetic flux. How will it oppose the change in magnetic flux? If we use the right hand thumb rule, it will create a north pole. Basically, if it is a north pole, it will repel the magnet, through which will oppose the electric field. And for it to produce a north pole, we can see using the right hand thumb rule, which is basically, if it needs to create a north pole, the current will be induced in this direction, anti-clockwise direction, through which the loop will provide a north pole. And if we are taking a magnet away from the loop, this is north of the magnet. Now if we are taking it away, then in such a case, it also needs, here as well there is a change in flux, and it needs to oppose the change in flux, due to which it needs to produce or stop this magnet from moving away. That can be done by producing a south pole here, and that can be in the direction of, and to produce a south pole the current should be in the direction of clockwise direction. That's about Lenz's law. Let's not go too much into it. And the minus sign indicates that comes from Lenz's law basically. Now combining equation 7.1 and 7.10, I mean this equation, this is 7.10 and 7.1. Okay, 7.1 basically is this equation where Vrms value, which is equals to Vm sine omega t. This value, we basically shifted this one this side. Now we wrote it as V by L. After shifting it this side, L we shifted down. Now we will get di by dt. Now dt also we can shift that side. We will get here, if we see, okay, this is the equation vi by dt, which is di by dt, which is equals to v by l, or vm sine omega t by l. Now equation 7.11 implies that the equation for I, which is a function of time, the current as a function of time, must be such that its slope di by dt is a sinusoidally varying quantity in the same phase as the source voltage and amplified given by Vm by L. To obtain the current, we integrate di by dt with respect to time. Okay, we basically just sent, or we multiplied dt on both sides. This dt get cancelled. There is a dt here. Now we integrate, and this integration differentiation cancel. It's not exactly like that. Integration differentiation don't get cancelled like that, but here we know that di, which is equals to just I, so we can assume it as they are cancelling. Anyway, leave that. Now we will get I, which is I average, which is equals to Vm by VL. That same equation there, same equation as here. We will get this one, and now we integrate, because peak value of voltage and inductance are constant for a given AC circuit, and I mean given AC supply and configuration of the circuit respectively. Because of that, they both come outside because they are acting as constant. The only variable here is sine omega t dt, now which we will integrate, through which we will get integration of sine omega t. Erase this and write here. Now if we take integration of sine omega t, following the integration, we will get sine omega t dt. If we integrate, is equals to cos omega t by omega. It is something similar to a chain rule in differentiation, where we get it in the numerator in case of differentiation, but omega here we will get in the denominator. That is how we got this, and basically just some placement here, where instead of writing omega below cos omega t, they wrote it beside L omega. And if we compare this equation, with I, which is equals to I, which is equals to Vm by R sine omega t, or prior to that, let's not write this yet, don't compare yet. Let's convert this cos omega t or minus cos omega t. If we want to convert a cos omega t into sine omega t, what we need to do is, we know the ratio sine 90 plus theta, which is equals to cos theta, or sine 90 minus theta, which is equals to cos theta. And depending on the quadrants, we can understand which signs to take. And so minus cos omega t, or basically cos omega t is there, Now this cos omega t, we can write it as sine 90 minus, not 90 plus, 90 minus omega t. We can write cos omega t is sine 90 minus omega t. This is a trigonometric ratio or trigonometric identity here. Now since the all the values, all trigonometric values at first quadrant are positive, this will also be positive. But now there's a minus sign here that they are taking inside. We know that minus sine x, which is equals to sine of minus x. Based on this formula, we can intake this minus inside the sine function, which we can write as sine of minus of 90 minus omega t, that they have directly written as omega t minus pi by 2, or 90 we can write as pi by 2, basically pi by 2 radians or 90 degrees, same thing. Now omega, instead, now when we multiply minus inside, we will get omega t minus 90. So now after obtaining I, which is equals to Im sine omega t minus pi by 2, from this equation, now we can compare to our resistive circuit equation. Or Im, it seems there is no need to compare here. Wait a second. Im value here is equals to V peak by omega L. Now if we see similarly, let's write here, in pure resistive circuit, Im value is equals to Vm by R. Now if we compare both equations, where Im, which is equals to Vm by R in a resistive circuit, and Im, which is equals to Vm by omega L in a inductive circuit, the only thing common are resistance and omega L here. So based on Ohm's law, which is very similar to Ohm's law, this is acting as some kind of resistance. The magnitude of omega L is a total resisting force in terms of ohms. Basically, the unit of omega L is ohm. It is a total resistive force in a pure inductive circuit, and it is represented by XL, and it is known as inductive reactance. This is called as inductive reactance. In case of a pure resistor circuit, which we will see later, it is, we will denote the value or resist as in a pure capacitive circuit there is no resistance. As such, there will be one more formula which we will also get a reactance, a kind of reactance, a reactance which is called as capacitive reactance. That is not here in the capacitive circuit. We will see this later. Now in the inductive circuit, where if we both compare this resistance and omega L, we can denote XL, which is equals to omega L, which is acting as a kind of resistance, and this resistance is called as an inductive reactance, and it's denoted by XL. This inductive reactance is basically the opposing force in a pure inductive circuit. That is all about this. Okay, that is why I thought of comparing it with the pure resistive circuit with resistance and omega L, where Im, which is equals to Vm by omega L, is the amplitude of the current. Amplitude meaning the peak value of the current sine wave. The quantity of omega is, omega L is analogous to the resistance, similar to the same as resistance, and is called as the inductive reactance, denoted by XL, where XL, which is equals to omega L. The amplitude of current is then Im is equals to Vm by XL. No need for this, I believe. Okay. The dimension of inductive reactance is same as that of resistance, and its SI unit is ohms or ohm. It is It is also a resistive force. We don't need a separate unit for it. It is also called ohm, and its dimension are also same as resistance. The inductive reactance limits the current in a purely inductive circuit in the same way as resistance limits the current in a purely resistive circuit. Both inductive reactance and resistance have only one thing to do, that is oppose and resist the flow of charges, or reduce or oppose the flow of current. So both are doing the same thing, so both are same kind of quantity. Inductive reactance is directly proportional to the inductance and to the frequency of the current. Based on this formula here, where xl, which is equals to omega l, we can say that higher the inductance of a coil, higher the uh, resistance of that coil. I mean, higher the reactance, inductive reactance of this coil. We can understand this logically by thinking that we know that the inductance, self-inductance is opposing the flow of current. It's in the opposite direction of the current. So the higher the resistance of the coil, higher the self-inductance of the coil basically, or higher the more the turns of the coil, more the change in magnetic flux. Based on that, more the potential opposing potential difference produced and more the opposing current produced, due to which the more the self-inductance of the coil, the more the opposing current produced, and the more the resistive force. And because of that, xl, which is inductive reactance akin to resistance, is directly proportional to l, that is self-inductance. As for why it is proportional to frequency, the higher the frequency, the more the higher the frequency. Frequency is basically 2 pi by t, meaning the time it takes for I mean angular velocity, not frequency. Angular velocity. This is omega is angular velocity. The faster the, we can just say that higher the angular velocity, the more times the rotation will take place in case of an AC generator. Like if we assume in case of an AC generator, then the faster we spin in case of a like AC generator, it's similar to a windmill. The faster the windmill spins, the higher the angular velocity, the more the current produced. Similar way, the more the current produced, the higher the magnetic flux changes. Because of that, higher the opposing current produced. Because of that, it is directly proportional to frequency. Okay, that's that. Limits current in purely resistive circuit. The inductive reactance is directly proportional to the inductance and to the frequency of the current. A comparison of equations 7.1 and 7.12 for the source voltage and the current in an inductor shows that current lags the voltage by pi by 2 and or 1/4 of the cycle. Okay, let's compare the equations here. Two equations they gave. Basically, we know the potential, potential EMF value, or V is equals to Vm sine omega t. This is from the start of the chapter. This is same for resistive circuit, inductive circuit, even for the capacitive circuit. This is the potential difference, potential at an instant of time. For an AC source, this is the potential for an AC source at an instant of time. But what is changing is current is changing. For I, for in a resistive circuit, I, which is equals to Im sine omega t. This is for resistive circuit. Now we are not talking about resistive circuit here. In here, but let's just focus here for a second. In a resistive circuit, both the angles sine omega t is equal. Because of that, we can say the phase difference, that is the angle difference between them, is zero and they are in phase. But as we know from before, in case of uh, Inductive circuit, that is not the case. In case of an inductive circuit, I is equals to Im sine omega t minus pi by 2. This is the reason we went through the headache of converting cos omega t to sine omega t minus pi by 2 to compare these both equations. When we compare, we see that we sine omega t, here the angle is omega t, and here the current angle, which is 90 degrees behind the angle of the potential difference. That means current is lagging voltage, it is behind voltage by an angle of 90 degrees. And in this case, we can clearly say current and voltage are not in phase. And let's observe the diagram here. If we see the diagram, this is the phasor diagram as well as the graph. If we see the graph first, let's see the graph first. Here if we see, or yeah, let's see the graph first. When current is zero, when potential difference is zero, current is at minus peak value, and at potential is peak, current is at zero value. As potential difference is reaching zero, current reaches peak value. As potential difference reaches negative value, current reaches zero, and as potential difference reaches zero, current reaches negative peak, and as potential difference again reaches peak value here, current reaches zero. Okay, this means at same time when they are in phase, like in a pure resistive circuit, the variation is same. Like when current is, like when potential is attaining a peak, current is also attaining a peak. When potential is zero, current is also reaching zero. But here, when they are not in phase, that is clearly not the case. They are not the same. They are varying. They are not having a same kind of variation at same instant of time. That is not happening here. And if we observe here, this is also a sine wave, and this is also a sine wave. They are just, it seems as though the current sine wave has shifted slightly forward. The current sine wave has shifted slightly forward. That is what lagging by 90 degrees is. We might be confused why it moved forward when they said it is lagging by 90 degrees. Because here if we see, even though if we draw this as well, or we don't need to draw that, when current is steadily decreasing here, and increasing here in the negative direction, the potential had already reached zero, meaning it is forward. Even though we shifted the wave forward, here current actually is at negative peak value, where in the race the potential had already reached zero. That is why current, we say, is lagging behind. Now let's see the phasor diagram. Now if we see the phasor diagram, is clearly different from the pure resistive circuit. This is the potential difference, and this is the current, and there is 90 degrees gap between them, and current is behind. If we assume that they are rotating in an anti-clockwise direction, that we can assume that current is lagging behind. That's all that we can see in the phasor diagram. phasor diagram of circuit, graph of V and I versus omega t. Okay, let's go back to reading. Now this figure what we saw just now shows the voltage and current phasors. In present case, at instant t1, the current phasor I is pi by 2 behind the voltage phasor V, and rotated with frequency omega counterclockwise, mean anti-clockwise, they generate the voltage and current given by equation 7.1 and 7.12 respectively, as shown in figure 7.6b. This one. We see that current reaches its maximum value later than the voltage by 1/4 of a period, t by 4, which is equals to t by 2 by omega. How we got that formula is, we know that omega, which is equals to 2 pi by t. Now t, which is equals to 2 pi by omega. Now if we divide both sides by 4, it will become 4 omega t by 4, which is equals to 2 pi by 4 omega. 1s are, 2s are, t by 4, which is equals to pi by 2 omega. This can be written like this as well, where we take 2 up. It's the same thing. You have seen that an inductor has reactance that limits current similar to resistance in a DC circuit. Does it also consume power like a resistor? Let us try to find out. The instantaneous power supplied to the inductor is PL, which is equals to IV, which is equals to Im sine omega t minus pi by 2 into Em sine omega t. Basically, we know the formula P with power, which is equals to I times V or V times I. We know the V formula, which is constant throughout some part of the chapter, and we know our current in the inductive circuit, which we just found out. Same formula which we use. Now PL will get as, okay, we did all work by converting this into sine omega t minus pi by 2, which we can again convert back to cos omega t minus cos omega t for easier calculation. So basically we will get minus Im Vm cos omega t sin omega t, and this we can simplify it if we multiply 2 on 2 and divide by 2. Now if we consider this formula here, 2 times of cos omega t sin omega t, 2 cos theta times sin theta. This formula is a trigonometric identity or trigonometric formula where sine 2 theta, which is equals to sine 2 theta, which is equals to 2 sine theta cos theta. Using this formula here, same derivation, we write it as this 2 will come here. We write minus Im Vm by 2 sine 2 omega t. Using this relation, we got that answer here. So the average power over a complete cycle, which is this one, where omega t is constant, we take it out, and we know that average of sine 2 omega t, if we do integration here, if we do sine 2 omega t, if we do integration where we take for a full cycle, I'll erase this and do it. Why we got this sine 2 omega t bracket like this is 0 is because they're basically doing integration there. When we integrate 0 to t for a full cycle, that is sine 2 omega t Now when we integrate it, we will get it as minus cos 2 omega t by 2 omega from 0 to t. Now again substituting here, applying the limits, or we can write this as plus, and this will become like this, cos 2 times omega times 0 by 2 omega minus cos 2 omega t. Since there is not enough space, basic word is not working right now. So let's just say, after solving this, after taking values and substituting omega, which is equals to 2 pi by t, after substituting this value, let's just say we will get whole thing equal to 0, and because of that this will become 0, and we will get that the power dissipated in an inductive circuit which is equals to 0. Power dissipated in an inductive circuit which is equal to 0. Since the average of sine 2 omega t over a complete cycle is 0, average power supplied to an inductor for one complete cycle is 0. And this is purely considering that the inductor does not have resistance, or it's a purely inductive circuit. It's a purely inductive circuit, meaning it does not have much resistance. It's basically negligible resistance. Only then will the power consumed will be 0. Now let's see a small example here. A pure inductor of 25 millihenry is connected to a source of 220 volt, which is the RMS value. Now find inductive reactance and RMS current in the circuit if the frequency source is 50 hertz. And this 50 hertz is actually a constant value in India. 220 volt, 50 hertz. Even when the question does not mention 50 hertz, sometimes you need to take frequency as 50 hertz. Okay, about that it's done. Now let's find inductive reactance. Inductive reactance formula is omega L, which is equals to XL, omega which is equals to 2 pi F, omega which is equals to 2 pi by T. Now frequency, which is 1 by T, so omega which is equals to 2 pi F, a formula which is very very important. Now, so basically XL, which is the inductive reaction, is equals to 2 pi F times L. We know the values of frequency, we know the values of inductance, self-inductance. We know pi is a constant value, 3.14. 2 is already a constant. Now substituting everything, we will get XL, which is approximately equal to 7.85 ohm. Now if we can calculate the RMS current in the circuit, which is equals to basically RMS current, which is equals to voltage by inductive reactance, RMS voltage by inductive reactance, which we will get as 28 ampere. Okay, let's continue possibly in next class.